So in this lesson, we're going to look at reaction mechanisms and basically how they are generated and how they've also dictated other things that we've learned in the unit so far. Okay, so what you need to understand is that basically the reactions that we've been talking about, even since last year, occur in a series of steps, and these steps are known as the reaction mechanism. Now, what you guys have normally been seeing is, a balanced chemical equation. And what you need to realize about that balanced chemical equation is that they don't actually tell us how the reactants become products. It's just basically a summary of the overall process. And because of this fact, that is why we're not able to use the balanced equation to actually establish our rate laws. We must use experimental data in order to establish our rate laws. And that's because the process summary that we're seeing doesn't necessarily indicate what's dictating the rate of that reaction. So elementary reactions are reactions that occur in a single event or step. Basically, it's a very simplistic step in a reaction. Okay, and in an elementary reaction, the number of molecules that participate as reactants determine the molecularity of the reaction. So if there's only a single molecule in an elementary reaction, you have a unimolecular step or a unimolecular reaction. If two molecules are present, even if they're two of the same type of molecule, you have a bimolecular reaction, and then termolecular reactions are obviously going to have three molecules. Okay, now what you need to understand is that getting three molecules to collide is actually very, very difficult. Having the correct energy and orientation is required in that step, and obviously that's going to have the correct orientation and all of that good stuff that we've already been talking about. And it's difficult to have that happen between two molecules. So it's extra difficult to have three molecules collide with the appropriate energy and orientation. So termomolecular reactions are very, very rare. And anything higher, like four or more molecules colliding, is basically highly unlikely. It's unlikely to happen at all. So elementary reactions are extremely useful in the fact that we can establish rate laws for these steps based on their equations. Okay, so based on the molecularity that we've observed. Okay, so if we look at the examples that we have here, okay, we have a single reactant going to products. The rate law here is going to be written as such. Okay. A bimolecular reaction. Okay, these are both examples of bimolecular reactions. Notice I have two reactants going to products. Okay, this is my rate law here. Notice the concentration of A squared, or we have this second order overall rate law here with A and B. Okay, if you sum up those two exponents. Okay, termomolecular examples, which are obviously a lot more rare than unimolecular, bimolecular, can be represented by the following rate laws. Okay, so look, elementary reactions allow you to write rate laws from the balanced equation in that step. Okay, now what you must remember though is that you cannot get the rate law, right, from an overall balanced equation. Okay, so remember, these individual elementary reactions, they're used to express mechanistic steps in an overall reaction. Okay, you can express rate laws for the elementary reaction steps, but you can't express a rate law using just the balanced equation for the overall reaction. So make sure you're making this differentiation. Okay, so they've asked us here to basically look at the reaction below. They tell us the following reaction occurs in a single elementary reaction and to predict its rate law. Okay, so basically they're telling us this is an elementary reaction here and to write the rate law for it. Okay, so basically what we would do here is we would write rate. K is obviously going to be equal to H2 plus Br2. Okay, this is a second order reaction based on this elementary reaction step here. Now, this is the proposed reaction rate law. However, what we actually find out experimentally is that the rate law is more like something like this. Which is very different than what we have expressed from the elementary rate law above. Okay, however, if you know that you're looking at an elementary step, okay, you can write a rate law. Now, the rate law that you propose must also match the rate law of the experimentally determined analysis of that reaction. So make sure that you are differentiating once again between the overall reaction and the individual elementary steps. Okay, and obviously the rate, whatever rate law you write, has to actually be supported experimentally. Okay, so some just vocab. The elementary step or elementary reaction is a reaction whose rate law can be written from its own molecularity. Basically, each individual step is going to have its own specific rate law that corresponds to it, its own K, all that good stuff. Okay, molecularity is a number of species that are actually interacting in that elementary step to produce the reaction. Okay, so having a unimolecular, bimolecular, termomolecular, etc. Okay, and then the rate determining step is basically something we need to understand moving into the next portion as we look at multi-step mechanisms. Okay, so the rate determining step, guys, is basically the step in a mechanistic process that is the slowest step. Okay, so basically you'll never be able to produce products at a rate faster than the slowest step within a mechanism. Okay, so multi-step mechanisms are basically a summation or a reaction sequence consisting of elementary reactions. And those individual elementary reactions express what's happening to the overall reactants and products that we see in the overall balanced equation. Okay, now for this specific reaction here, the mechanism is thought to proceed by the following steps. We have NO2 and NO2 colliding to give us NO3 and NO. This is our slow step. Okay, and then NO3 then collides with CO to give us NO2 and CO2, and this is considered the fast step. Okay, now both this step and this step are the elementary steps or the elementary reactions. And basically, these elementary steps must always sum to the overall reaction that's being looked at. So in this case, NO3 and NO3 cancel. One of these NO2s and one of these NO2 cancel to give you this overall equation. I guess another thing that needs to be mentioned is the NO3. Okay, NO3 is produced during the slow step and then used up during the fast step. Basically, it's a species that isn't technically a reactant or product because it's basically formed and consumed during the reaction progression. Okay, so understand that also intermediates aren't transition states. They're not that species that we see at the top of our reaction progression diagrams. When we've looked at the Arrhenius equation, those are not the same features. In fact, many intermediates can actually be isolated, where a lot of transition states, or rather most transition states, are so short-lived that they're not able to be isolated. Okay, and the last thing I obviously want to point out is notice here is the slow and fast step. Okay, so remember we talked about that rate limiting step a little bit ago. Okay, the slow step is the step that's going to limit the rate of your reaction. Okay, and we'll talk about how that comes into effect here in a minute. Okay, but please understand that the slow step can either be the first step or the second step. It doesn't always have to be the first step in that process. And we'll learn how to deal with the various positions of the slow step. Okay, so the conversion of ozone into oxygen is proposed to occur by the following mechanism. Okay, so this mechanism down here is basically showing us this conversion process, okay, in its elementary reaction steps. And so they want us to do a few things with this mechanism. They first want us to describe the molecularity of each of the elementary reactions in the mechanism that's down here. Okay, so in this case, we have a single ozone atom reacting to give us product. So this is a unimolecular process. Okay. The second step down here that we see, it consists of two molecules interacting. So this is a bimolecular process. So we've described the molecularity of each of the elementary steps in the reaction below. Okay, and they want us to write an equation for this overall reaction. So remember that the reaction here, or the reaction mechanism steps, have to sum to the overall reaction that's being looked at. Okay, so basically oxygen and oxygen cancel. They basically show up on opposite sides of the arrows, and that gives us the following reaction as our overall reaction. Okay, sorry, it should have been a 3 up here. All right, and then the last thing they want us to do is to identify the intermediate. Remember, the intermediate is a component in the reaction that isn't something that shows up as a product, isn't something that starts out as a reactant, but basically is produced during the mechanistic elementary reaction steps and subsequently used up in one of the other steps. Okay, so in this case, the oxygen atom here is what's actually being used up. So oxygen is our intermediate because it's produced during the first step and used up in the second step. Okay, so now that we've determined molecularity and intermediates, let's go ahead and look at some more details of multi-step mechanisms. Okay, so reaction mechanisms have some requirements that must be met in order for it to be deemed an acceptable mechanism. Okay, so the first thing is that the sum of the elementary steps must give the overall balanced equation for the reaction you're actually looking at. Okay, so we've already kind of looked at this on the last problem that we did. So it's pretty straightforward. Everything should sum up to the overall equation. Okay, the second requirement is that the mechanism must actually agree with the experimentally determined rate law. Okay, so you can't have a rate law that you're getting from the mechanism that totally doesn't support anything about the actual reaction progress that is seen and recorded experimentally. So here's an example of a reaction right here. Okay, this is an example of a reaction mechanism. Okay, the first thing we're obviously going to look at is whether or not it fulfills the first requirement, which basically do the individual steps sum to the overall reaction. Okay, and if we look at this, NOBr2 cancels, we end up with 2 NOs, a single Br, and 2 NOBr. So that is this overall reaction. It does sum to these mechanistic steps do sum to the overall reaction. So you subsequently meet the first requirement. However, the second requirement is a little bit trickier. So we're going to look at how to analyze the second requirement. So basically, in order to determine if a mechanism agrees with the experimentally rate law, okay, we must consider basically if the first step of the slow or rate limiting step is the first step in our mechanism, or if the first step of our mechanism is a fast step. So basically, depending on where the position of the slow step is, that's going to basically dictate our approach to figuring out the correctness or the matching of our mechanism with our experimentally determined rate law. So let's go ahead and let's look at an example with a reaction mechanism with a slow initial step. Okay, so this is the reaction we're looking at here. Notice we have our experimental rate law, which is second order with respect to NO2 here. This is what we figured out from analyzing our data, just like we have done in previous lectures and activities. And the proposed mechanism is as follows. Okay, so the first requirement, obviously, is to figure out if the sum of these two reactions sum to the overall equation. Okay, and if we look at this, obviously NO3 and NO3 cancel. Okay, one of the NO2s cancel. So the overall reaction mechanism is provided by the summation of the individual steps. So the first requirement is met. Now the second requirement is that the rate law that's determined from this mechanism must be matching or must be supported by the experimental rate law that has already been determined. Okay, so how do we do this? Well, what we do is we take the slow step in the reaction mechanism, right? And we utilize the fact that it is an elementary reaction and write the rate law associated with that step. Because remember, the rate of the reaction is going to be dictated by the slowest step, because no products can be produced or no reactants can be used any faster than the slowest step. Okay, so in this case, if we look at this slow step and we write the rate law associated with this slow step, we are going to get the following. Okay, remember it's a bimolecular reaction. Okay, the number of molecules determine the molecularity and subsequently determine the order of the rate law for that step. Okay, so now that we've written the rate of this slow step, we can then compare it to the experimental rate law. In this case, it matches. Okay, so this mechanism is considered a plausible mechanism. Okay, so remember, we have to make sure that the overall steps of the proposed mechanism sum to the overall reaction from the balanced equation. Okay, and the second requirement is that the rate law that you determine using the rate determining step must be supported by the experimentally determined rate law. So this is a plausible mechanism, and this is how you do this process when you have a slow initial step as the first step in your proposed mechanism. So when we're dealing with mechanisms that have a fast initial step, we have a little bit more complicated process in order to figure out if our mechanism is actually a plausible one. Okay, so once again, we still have our overall equation. We have our experimental rate law that must match our rate law that we determined from our mechanism. Okay, now obviously the first thing to always look at is if the sum of our mechanism steps add to our overall reaction. So NOBr2, NOBr2 cancel. Okay, we end up with 2 NOs, a Br2, and 2 NOBRs remaining. Okay, so the first requirement is met. Okay, so now we need to check and obviously see if the slow step mechanism actually supports the experimental rate law. So what we would do is we would write the theoretical rate law based on this slow step. Okay, and you can see that that is provided right here. Okay, so we have our theoretical rate law based on our slow step. Now, obviously, we know that this does not match what we have as our rate law up here. However, what we need to take into account is the fact that this rate law actually depends on the concentration of an intermediate. Okay, so notice there is an intermediate in this rate law for the slow step. Now, intermediates can have slow or unknown concentrations, and basically we don't really want to express our rate law with respect to NOBr2. So we're going to make a few assumptions about the presence of NOBr2. And basically look at our rate law with respect to only non-intermediate components. So what we assume is that basically we end up with a dynamic equilibrium between the forward and reverse reactions in the fast step. Okay, and basically what we end up getting is basically a relationship between our NOBr, which is our intermediate, and our reactants. Okay, so basically the rate of this forward reaction is written here, and the rate of the reverse reaction, okay, the NOBr2 going back to NOBr2, NO and Br2, excuse me, is seen here. Okay, so basically we're assuming that this forward and reverse reaction is able to occur, partially because obviously since this is the fast step, we produce some of this, which then starts lying around, okay, and then we subsequently, because the next step is the slow step, there isn't really a chance for this to get used up super quickly. So basically there is a good chance that it could possibly revert back to its original reactant form. Basically we anticipate some sort of equilibrium to be set up so that there's kind of a constant concentration between these two. So we relate the two rate laws of the forward and reverse reactions and obtain this. Okay, we then take this equality that we see here and solve for NOBR2. Okay, so notice what I've done is I've divided out the rate constant on this side over here. Okay, so NOBR2 is equal to K1 over K to the minus 1 times NO times BR2. Okay, so we now have a relationship between this intermediate and our reactants. Okay, so we can then take this value of NOBR2 and subsequently what we've set it equal to and plug it into our theoretical rate law of our slow step. Okay, so basically instead of plugging NOBR2 into here, we're going to plug in what NOBR2 is equal to, which is K1 over K to the minus 1 times NO times BR. Okay, so we plug that in and we now get this rate law here. So K2 times K1 over K to the minus 1 times NOBR times NO, which was what we already had there. Okay, so basically when we compress this down, we end up with our rate being equal to this. We now see that our rate law, okay, from our mechanism actually matches our experimental rate law. So the mechanism that we saw in the beginning of this problem with the fast initial step mechanism is actually supported as being a plausible mechanism based on this reaction and the analysis we just did. So something to note about reaction mechanisms, okay, obviously I've been using the word or the phrase that the reaction mechanism is plausible. What you need to understand is that a mechanism can never be proven absolutely, okay? So basically, a mechanism can never be proved, it can only be disproved. However, we can look at mechanisms and say, hey, this suggested mechanism is supported as being plausible. Okay, and basically we can look at a quick example. All right, this is a reaction that we're looking at. Okay, the experimental rate law is as follows. Okay, if we look at the overall sum of these reactions, that first requirement is met. It gives us this overall equation. Okay, and if we look at the first initial step here, the slow step that is broken down in this mechanism's elementary steps, okay, we notice that if we were to write the rate law for this slow step, it would match our experimental rate law. So this is considered an acceptable, or excuse me, a plausible mechanism for this specific reaction. In that same thought process, okay, this reaction mechanism is also considered an acceptable mechanism or a plausible mechanism. Okay, these steps all sum to the overall equation. Okay, and the slow step, if we write out the rate law for this specific step, okay, we end up with the same rate law as what we see in the experimental rate law.